MSA for continuous data. What is MSA for continuous data? Let's talk about MSA, or Measurement System Analysis, for continuous data. MSA helps us evaluate whether our measurement system is capable of doing three key things. First, it must be able to accurately measure continuous variables. These include things like time, length, weight, or pressure. Anything that can take on a wide range of values on a continuous scale. Second, it should be able to detect process variation, meaning it should help us see when a process changes or shifts. And finally, it must do all this without introducing too much measurement error. A good measurement system gives us reliable data that reflects the actual process, not noise or mistakes from the tools or methods we use. Now, remember that continuous data means values that fall on a scale with infinite possible values within a range. They're not limited to fixed steps. Here are a few real-world examples of continuous data. The diameter of a bolt measured in millimeters, delivery time recorded in minutes, or temperature in degrees Celsius. Why MSA for continuous data? Now, let's understand why we even need to do MSA for continuous data. The first thing to remember is this: every measurement system adds some error or variation. No tool is perfect, whether it's a stopwatch, a thermometer, or a caliper. So, our main goal with MSA is to separate the two types of variation. How much of the variation is actually coming from the process itself? And how much is coming from the measurement system? That is, the tools, methods, or even the person taking the measurement. This is critical because if your measurement system is unreliable, if it's adding too much error, then the data you're using for analysis might not reflect the real process at all. Here's the key message I want you to take away. Never assume your measurement tool is perfect. Prove it. Because if you don't, and your system adds too much variation, you risk making the wrong decisions based on flawed data. Let's talk about measurement variation, which is a critical concept in quality management and process control. Measurement variation refers to the variability that arises from the measurement process itself, rather than the actual process being measured. It's important to understand that even a stable process can appear unstable if the measurement system is not reliable. There are two primary sources of variation in a continuous measurement system. 1. Repeatability. This is the variation when the same operator uses the same equipment to measure the same part multiple times. In other words, it's the consistency of results under identical conditions. 2. Reproducibility. This type of variation occurs when different operators use different equipment, but measure the same part. It reflects the impact of changes in people and tools on the measurement. Together, these two components form the total measurement variation, expressed in the formula. Total measurement variation equals repeatability plus reproducibility. Our goal is to minimize both repeatability and reproducibility errors. A good measurement system should show minimal variation regardless of who measures, with what, or when. Understanding and reducing measurement variation is essential for reliable data and effective decision-making in any quality improvement project. In this section, we focus on measurement system analysis, or MSA, specifically for continuous data. These are measurements that can take on any value within a range, such as length, weight, or temperature. When we evaluate the effectiveness of a measurement system for continuous data, there are two primary tools we rely on. 1. Gauge repeatability and reproducibility, often referred to as gauge R and R. This tool helps us understand how much of the observed measurement variation is due to the measurement system itself. It includes repeatability, variation when the same person measures the same item with the same equipment. Reproducibility, Variation when different people use the same equipment to measure the same item. Second test retest, repeatability study. This is a simpler study that looks only at repeatability. It involves a single operator measuring the same part multiple times under consistent conditions to evaluate the consistency of the results. These tools are fundamental in validating whether our measurement system is reliable enough to support process improvement initiatives. Let's now take a closer look at both tools to understand how and when to use them. Let's now look at a practical example of how a gauge R&R study is conducted in a manufacturing setting for continuous data. Step 1. We start by selecting 10 metal rods, each with different diameters. This allows us to capture a representative range of variation in the parts being measured. Step 2. Then we have 3 inspectors, or appraisers, who will measure the diameter of these rods using the same caliper. It's important that the same measurement instrument is used to ensure consistency across readings. Step 3. Each inspector will measure each rod twice. This repetition is key to assessing the repeatability of the measurements within each operator, and also helps evaluate the consistency across operators. At the bottom of the slide, you can see an example of how the data might look. Each part is measured twice by all 3 operators, and the results are recorded in a table format. For example, for Part 1, Operator 1 recorded 15.21 and 15.20, Operator 2 got 15.21 and 15.20, and Operator 3 recorded 15.22 and 15.24. This data matrix is then analyzed statistically to determine how much of the variation is due to the measurement system versus the actual parts. This example helps us visualize how the gauge R and R study is structured and why it's crucial in evaluating the reliability of our measurement process. Now let's talk about what leads to high measurement error in a process. Measurement errors can significantly affect the reliability of our data. This slide highlights some common causes of high measurement error. Poorly calibrated equipment. If our tools or instruments aren't properly calibrated, the measurements they provide won't be accurate. This is a technical issue, but a very frequent one. Inconsistent measurement methods. When the method used to take measurements is not standardized or varies between operators, we get inconsistent results. This is often due to lack of documentation or unclear procedures. Environmental factors. Conditions like lighting, noise, and temperature can interfere with measurements, especially in sensitive environments. These need to be controlled or standardized as much as possible. Lack of training. Even if we have the right tools and methods, untrained or poorly trained staff can introduce errors. Training ensures consistency in how measurements are taken. The takeaway here is that both human and technical factors contribute to measurement error. By addressing these root causes, we can significantly improve the reliability of our measurement system. Now let's talk about some key do's and don'ts when conducting a measurement system analysis, or MSA, specifically for continuous data. Starting with the do's. Always use representative samples that cover the full range of process variation to ensure your results are valid. Randomize the measurement sequence to minimize any systematic bias. Make sure your measurement procedures are standardized across all operators to maintain consistency. It's critical to calibrate your equipment before the study to ensure accuracy. Train all operators beforehand to avoid inconsistencies in measurement technique. Use specialized software like Minitab or JMP to analyze your data correctly and effectively. If your gauge R and R results are poor, don't just accept them. Investigate the root causes. And finally, use a sufficient number of repetitions in your study to ensure the results are statistically reliable. Now the don'ts. Don't skip MSA just because you're using expensive equipment. Price doesn't guarantee accuracy. Don't allow operators to compare results during the study, as it can bias the outcomes. Don't ignore environmental factors such as lighting or vibration, as they can impact measurements. Don't assume your measurement system is good enough without supporting data. Always back it up with numbers. And don't use only one operator. You need multiple operators to assess reproducibility effectively. By following these guidelines, we can ensure the accuracy and reliability of our measurement systems, which is foundational for any quality improvement initiative. This slide highlights why measurement system analysis, or MSA, is so critical in Lean Six Sigma. First and foremost, data drives decisions, and in Lean Six Sigma, we rely heavily on data to make informed choices throughout our improvement projects. However, if the data we're basing our decisions on is flawed due to measurement error, then the quality of our decisions is compromised. Measurement errors can directly impact 1. Capability analysis. If your measurements are inconsistent or inaccurate, your capability indices like CP and CPK won't reflect the true performance of your process. 2. Control charts. These are only useful if the data plotted is reliable. Otherwise, you may see false alarms or miss actual issues. 3. Process improvement actions. If we misinterpret the data, we might address the wrong root cause or implement changes that don't actually help the process. There's a great quote on this slide. If measurement error is too high, you're chasing measurement error, not process variation. This means that without a proper MSA, you might think there's a problem in the process, when in reality, it's just the measurement system giving you faulty data. So, in essence, MSA is not just a checkbox. It's a foundational step to ensure the integrity of your data before you make any critical process decisions.